device, which means which is the I phonon by the power what you put. Okay, so there that the responsivity goes to almost 10 to the power 6, which is indeed very high. But the problem is that this is a exfoliated device and you cannot scale it. Okay, so to do to improve further, what we have taken graphene and TMD hybrid. So why we have taken graphene TMD hybrid? Because graphene, we took CVD graphene, as Venkat was mentioning as well. So CVD graphene has a lower mobility, but still it's quite high compared to the conventional 2D semiconductor. Like you can see, one of the CVD graphene has a mobility of 2000 centimeters per whole second, and although its band gap is 0. And TMD materials, typical mobility when we started at that time, typical mobility on silicon dioxide surface is 10 or of this range, like 10 centimeters per whole second, if you get a good device. But it has a band gap of 1.3 and to 2.1 in this range. So this large scale integration is possible in this configuration because you can take a CVD graphene, and if you can make a nanostructure of this 2D TMD, you can just spin coat it or drop cast it, and you can get a device. So this was our idea, and then what we do, we make this. First we started this project with WS2 nanosheets. So WS2 nanosheets, if you take a absorption spectra, then what you can find, this is the absorption spectra, and you can see a broadband absorption spectra, right? So you can see UV to almost 300 to 800 nanometer range, you can get full absorption. Okay. So why do you see these 4 peaks? You can see A, B, C, and D peaks. So the origin of A, B, C, D peaks are mainly from this band structure. You can, if you take like a large area of TMD materials, then typically you will find A and B peaks. Okay, A and B comes from this split valence and conduction band. Okay, so you can see this AB excitation originating from this thin split of band. Now, the C and D peaks, these are very interesting, and this comes when you have, if you go in this side, lambda to A gamma, in this range, this band structure is almost parallel. And from this region, one can expect C and D excited. And when you make nanostructure, people have found this intensity actually goes very high. So I'll not go into the detail, but the main importance is that you can make this nanostructure, you can get a broadband absorption, and which is important for us. If you make a device, you should be able to make a broadband photodetector using this kind of device, this kind of sample. Now what we have done, if you take just pure nanosheets or quantum dot, you can even make quantum dot. And if you spread it, you cannot make a channel like this, right? So to make a channel, what we have combined, we just broadcasted this on a so like this we make a CVD graphene and nanosheet, the quantum dot or nanosheet. So first thing what we observed that this is the current versus gate voltage curve of a pure graphene signal, the graphene sample, like this black curve, and you can see this graphene is heavily doped. You don't get any Dirac point. But whenever you are putting this nanosheet or nanostructure, you can see always you start getting this Dirac point, okay, or charge 120 point, and that is because you have a charge transfer from these nanosheets to the graphene. Okay. We have performed the response measurement, and you can see interestingly that you can see a nice photo response in like almost 365 nanometer to 633 nanometer devices. Okay. Another important thing is that you can apply gate, so you can tune this photo response. For example, if you measure the responsivity, you can see that responsivity goes from positive to negative value. That means both electron and hole type of carrier are you can tune, use photocurrent you can tune using this kind of device, and that is coming purely because of the hybrid band structure. So when you combine graphene to this CMD, for example, if your gate voltage is negative compared to some threshold voltage, then you can see the your band bending is one side, right? This direction. Now, when you are having when you are putting gate voltage in the high positive gate voltage, now your band bends in the other way. So in this way, one time you can have a volt transport, another time you have a electron transport. Okay, so that's how you can get a tunable photodetector just using this hybrid device. Okay, so then what we have shown, if we can actually make very nice quantum dots. So you can really see this kind of quantum dot of 5 nanometer or below, and also you can make nanosheet. So if you compare this morphology, you can clearly see expectedly that in case of quantum dot, the response is much higher, and which you can explain, which actually Professor Priya Mahadevan's group explained using this theory that you can enhance this photon response just by due to the confinement effect, which is expected. But we have shown experimentally that it is indeed the case. So using this, we can actually demonstrate this broadband photodetector. Now we ask the question: what is the role of these defects? Okay. So for this, what we have done, we can actually make this this alloy also in the nanosheet form. Okay, like you can make this alloy MOS2 to MOS AC2 by changing the MOS SX and AC1 minus X. Like you can change the concentration, vary the concentration between AC, S and S, and you can continuously go from MOS2 to MOSC2. So like that, what the idea is that you can tune the vacancies. Okay. So let's see what happens. So we make the same type of device structure. Before that, this is the characterization of this alloy. So you can see this like a PL, like the absorption spectra of this kind of alloy by varying this X. Okay. Now you can see all this A and B exciton, and you can continuously see the evolution of the PL from MOS2 to MOSC2, and this is the Raman spectra. So you can see you are going from MOS2 to MOSC2. Okay. So that is also you can very nicely control. Now what we have done, we have made the same type of photodetector device just on graphene and this alloy, and we check what I will go to the results. What we found that the performance is enhanced only in case of MOSAC when is both are 0.5. Okay. So another important parameter which I should mention in this photodetector is the noise equivalent power. So noise equivalent power is very important in this kind of 2D devices because typically it tells you how much weak light you can detect, right? So in this 2D kind of devices, the 1 over F noise is very high because it's very close to the surface. So interfacial trapping detrapping. This is root over of SI, the power density by the responsivity. How much sensitive to your light. So this parameter is very important, and this chart, the detectivity, is root over area by the NET. It tells you the weak light detection capability. So what we found that in our devices, you can calculate this NET, and it's reasonably good in this kind of device. Okay. So I told you that we could get a best performance in case of MOSAC. So now we don't have a detailed theoretical understanding, but what literature actually there are not much work done in this area, like understanding really the defect levels. Okay. So what we can tell that from the literature that whenever you are having you have the sulfur vacancy or selenium vacancy. Now these are actually deep level defects. Now when you are making this MOSAC, this just shift the band structure without shifting the defect level. So you can see that deep level defects actually going to the shallow level defects. So that actually enhance the performance of this optoelectronic device. This is our assumption, this is the understanding based on this theoretical calculation, in literature. We are trying to develop this DLTS technique now, so deep level transient spectroscopy technique, to understand really the defect level. This light matter coupling in this kind of device. In the next, what we have tried to enhance the photo response by light matter coupling. So what we have done, we have taken, for example, silver nanoparticle. So as I told you, silver nanoparticle should have plasmon, like this kind of dipole plasmon. It can create if you shine light, and this plasmon frequency is in the range of 400 nanometer. Now this in WS2, we have used WS2. It has also, you can also create this excitant, as I mentioned earlier, right? So this electron hole dipole. Now both these can interact if you can make it very close to each other. Now what will happen if you can okay, another important thing is that you cannot put silver directly on WS2 because it will react immediately at room temperature. It will react and it will not be chemically stable. It will form Ag2S. Now to protect that, what we have done, we have put a PVP capping layer, and that you can chemically control, and that is very interesting. You can put a 2 nanometer to 5 nanometer PVP capping layer, and you can actually you will not have any charge transfer between this. You will only have energy transfer between WS2 and this one. But interestingly, what okay, just to remind you that if you make this kind of excited plasmon coupling, you can enhance this absorption through Purcell effect, which was discussed in detail, but this is just you can enhance the electron light matter coupling. So what we have done, we have made it, this is a WS2 nanosheet, and we can put this silver nanoparticle, embed this silver nanoparticle on this nanosheet. And what you can do, you can see these are very close to each other, and you can see this very nice WS2 nanoparticle. This is a TEM image, and you can clearly see signatures of light matter coupling. For example, in the Raman spectroscopy or in the PL spectroscopy, you can see this signature. Now, this one of the main signature is that, for example, if you see this PL spectroscopy, then you will see this WS2 First of all, the PL signal enhances very much, and compared to the pure WS2, and there is a blue shift, which is opposite to the WS2 case. For example, in WS2, if you shine light, you will find you can create more triumphy. So that's why you will have a red shift. But in case of WS2, WS2 AG, you will have a blue shift because you can actually this is due to the light matter coupling. Okay, so this is one of the proof that you can make a nice dipolar coupling between this excitant and plasmon, and you can get all the signature. So what we have done, we have actually created the similar kind of photodetector device. Our device structure is same, graphene and this kind of hybrid. And what we have found, very nice demonstration of this enhanced photoresponse, like in case of this graphene WS2 silver hybrid, and you can get a better photoresponse compared to the pure WS2 graphene WS2. And we can explain this using the this Thomson-based simulation, just solving the Poisson's equation. It matches well with the theoretical prediction. Okay. So in the last couple of minutes or so, I will discuss our very recent work on the